Okay, students, this is Mr. Cooker, trying to help you all get some marks in your investigative project. And I'm bending over backward. I'm just point out some changes that you ought to make. Now, first of all, let's get down to the structure of the investigative project. This is something you should have done in Form 5. I just want to touch on something here, okay? In investigative project, there's a particular structure, there's a plan and design part, which has to do with the hypothesis, your aim, your materials and apparatus, a variable stated, method, results, precautions and limitations and assumptions and so on, and you must have your expected results and how you plan to treat those results. That is the part that's going to be a plan design. It's with 12 marks. Your A&I is also with 12 marks and has to do with after having done the lab, how you treat the results, your discussion, what you call the limitations and sources of error, reflection, show relevance of the experiment to real life and so on, impact of knowledge gained from the experiment, how can the experiment be changed and improved, these are things you're looking for. And of course you have a conclusion. The total is 12 marks as well. Now, let's get down into the heart of the project and see if you can get it to look anything like this. Now, when I give you a problem statement, this is what it was. And what I had an introduction, and that was, in this video here, it's bordered in green. And in that introduction, what I tried to do, I tried to give you information to furnish your reflection. If you use the information that correctly, you can furnish your reflection. The lab is basically about projectiles and energy storage systems, right? And energy conversion, of course. So, let's get down to the meat of the matter. So we asked to do what? To plan and design an experiment to determine the behavior of an average rubber band of a particular brand under load, examine its elasticity, observing especially whether its length under different loads vary if the loads are increasing or decreasing. You have to design to determine how energy stored in it varies with the extension, that is in bold, and in so doing also plan and design a procedure where we can determine the trajectory of a projectile of fixed mass fired from an elastic energy-based system at an angle of 0 degrees to the horizontal. Part B, which would be carry the experiment, explain when necessary any deviation from the predicted trajectory and what can be done to compensate for it. That's what they call the sniper's problem. Right, so what we have here now, I gave you a suggested list of equipment that you could have used. Right, so let's get on to it. Right, so let's look at the first part. You have to plan. Okay, you have to plan design to determine how energy stored in the rubber band when being stretched varies with the extension. Okay, so I want to go up quickly to look at something here. Sorry, down. Alright, this is the mark scheme I would have had for my plan design. This is the implementation, this is the plan design. Right, so on the left, in this column here, you have the things I was really looking for in the plan design. Let's take a quick look at it. Okay? Right, so student chooses appropriate apparatus. Student has a drawing of suitable apparatus to correctly determine the tension in the rubber band. Student appropriately sets up apparatus to determine the extension of the elastic member or rubber band. Okay. Student appropriately sets up apparatus to determine the extension of the elastic member or rubber band. So you must have a diagram or something showing how you're going to determine the extension. Diagrams are important and they save you a lot of writing. Student repeats experiments, repeats measurements. Well, I might repeat it for more than one rubber band, right? In a plan design, you can write that because the problem statement mentioned the average rubber band, right? If you look there, of an average rubber band. So I might, in my plan design, mention, I did it with more than one rubber band basically. I'll repeat it. In implementation, that's not so important, right? But in your plan design, I think that would help a bit. So let's go ahead and see what else we have here. Right, no, this is A&I. P and D, right. Student does readings with loading and unloading, and you'll see the reason why, because the graph has a pattern of loading and unloading, and you'll of course use that to comment in the A&I. It shows the difference in the patterns when loading and unloading, and explains how hysteresis affects your results. Students correctly sets up apparatus to launch projectile at 0 degrees to the horizontal using a level or plumb bob and set square or something. Yeah, you have to show me how you're getting this thing level. How you're launching it. So you must have either a level or a plumb bob or whatever. Well, I showed you what to do already. Student designs a workable method to determine y displacement at the value of x displacement. This has to do the second part of the plan design, where you have to actually find a trajectory. And then student clearly outlines a method to estimate or determine the energy of projection on launching. This will involve, of course, your graph. And then, of course, student shows how they determine the velocity on launching. And of course, it involves some equations, manipulation of some equations. And of course, student plans to use at least 2 launch velocities. Right? So, to show a pattern, you must have more than one. And then you have a total mark here, and the marks were miserable in the class. Miserable. Right? For all those criteria, these are how the marks looked. So, let's get on to it. Let's get on to everything that we have to do as a plan design. Okay. So, let's just go back a bit and see what we would like to do. Now, you want to determine the behavior of a rubber band under load. Now, you could either do a load against length or a load against extension graph. Right? But from the time you get this experiment, you decide to determine how the energy stored and varies with extension. It makes sense getting the load against extension. So the graph you'd use will be a load against extension. This is basically a problem starting. You want to get the effect of the load while you're loading up and while you're unloading. Okay? So, it's an experiment to do just that. Right. Then you have to find how the energy stored in it varies with the extension. So let's get on to that once, right? Okay. Here we are. If I add a rubber band in its natural state, this is natural length. If I add energy, add a load on it, or I put a force on the ends of it, it's extended and energy is stored. Well, in the experiment, if you looked at your if you look at the structure of what you expect to do in the investigative project, you must have some variables. What is control, what is manipulated, what is responding. So we had 2 parts, and the first part we want to find how the load varied with the extension, how the extension varied with the load, sorry. So what you're going to control, of course, you're going to control, you are going to control your rubber band. You can use one brand of rubber band. You'll keep that fixed. What you're going to manipulate, of course, is the load. You're going to add load to that rubber band. And what you're going to look at, you're going to look at the extension. So I do expect to see a diagram showing me some kind of retort stand holding a ruler and that kind of thing, and a nice neat diagram at that. Okay, so you need a rubber band of a fixed brand, because right, and then of course, as I said, you may want to repeat for a similar rubber band. Okay, so those are basically your initial variables, right? Alright, so let's go back to that. Alright, so we're looking at what really ought to happen. So let's see. Now we're going to find out how its extension varies with the loads. And we also want to find out how energy is stored in it varies with extension. So let me quickly do the energy part quickly. So as we add load, you can try and work out the extension. On the extension, energy varies with extension. Normally, this is the formula we use. Energy stored in any system that's being stretched by deformation is the integral of f dx, always true. So area bounded by the graph and the extension axis, the point where extension is 0 and equal x. Right? This does not apply, Hooke's law. If f is equal to kx, then it would have been equal to this. Energy should be equal to this. But this doesn't apply to rubber. So I just want to quickly look at the diagram. Quickly look at the diagram to show what actually happens. Now, quickly, stress strain curves. This has to do with Young's modulus. We looked at all that in class. And here we're looking at the typical curve for a metal. That's the curve for a metal. Now we're not using a metal, using a rubber band. But as you add load, it extends in this way. Incidentally, what is strain? Strain is force per unit area, and stress is force per unit area, and strain is extension per unit length. So if you look at it really, if we ignore the effects, or we actually have F here, the force or the load, and we have E here, the extension. This L here is a constant, it's really the original length, and this A here is the cross-sectional area of the rubber band. Okay, this does vary, but I just want to show the similarity between this graph. Normally a stress-strain graph looks very close. It resembles this graph always closely resembles, for any substance, it always closely resembles a force against extension graph. It doesn't have a similar shape. Okay, for obvious reasons. The L is original length, that's just a constant, and in most cases for the wire, the area of the wire kind of remains the same. Okay? Now, in our lab, however, we were not working with metal, we were working with rubber. As you can see here, with rubber, our graphs has a particular shape. We expect to get a graph like this. As we add, we can actually basically say we could substitute. You can basically say we could substitute for stress against strain a graph with quite a similar pattern. A graph of force against extension, and the shape will look very much the same. Right? This is what happens when you're loading, and this is how the graph pattern the graph follows when you're unloading. Okay, so I haven't said that much. This is the graph that we expect to get. Remember I said stress is force, same kind of force here, but this is over area. So the constant numbers that are being asked will be different. And then strain is extension over original length. The original length is always a constant. So you can see where the graph has basically the same shape, strikingly similar. Right, so we're going to do this graph here. We're going to do this graph here for our lab, force against extension. Why? Area under the graph actually gives you the energy stored. So I haven't said that much now. You have to set up your lab to actually get those measurements, right? You set up your lab to get those measurements. So you have your rubber band. You're going to change the load by using the stacked masses, and you're going to absorb the extension. You're going to record that in a table. Okay, and analysis and interpretation of results and so on. We'll come to that later. So let's go and see what we have here. We also looked at that and so on. Now, the second part of the plan design, we were asked to second part. So incidentally then, I should say that actually answers the first question. The first question basically, if I want to determine, right, if I want to find out how length varies with the loads, just the process of obtaining that graph, force against extension, will show how length varies with the load. The varying length is actually the extension, right? The variation in length is due to the extension, right? So the obtaining of that graph is what you're going to explain, right? With a particular brand of rubber band or whatever. That's what you're going to explain in the first part of your plan design. The second part, you have to also try to determine, how energy stored varies in it with the extension. How does energy vary with extension? We just touched on that, right? Energy varies with extension. Energy is always what? The area bounded by the graph and the extension axis and so on. So I have the load against the extension, and I do the graph, I load it up, I unload it. What I would realize, I realize that the area under the graph, let's say, let's do a dynamic one more time. Okay, so let's say this is the graph and you're loading up. If you load up to this extension E1, then the area under the graph, area on loading up will be followed by the loading curve. Up to E1, you come down here, and then here. That area there will be the energy stored in the rubber band then. Now, if I extend the rubber band extension E2, the area under the loading graph, that area there, by those boundaries, that area will be the energy stored in the rubber band then. If, however, I start to unload from that point, let's say I load up and look at extension E2. Okay, that means the force on the load has to be this value here. When I start to unload, it will follow a different curve basically. It will follow a different curve. Just as when it's loaded up to here, you unload, it follows a different curve. And so, really and truly, the actual energy available, right? So if let's say, that's when I load up, this is why when I unloaded, I got a shade look like that. Right? So what actually will happen will be something like this. I load up, let's say I load up to this point, and I started to unload from this point. What I might get will be a pattern that looks like this now. When I unload. And the actual energy I'll have access to will be this energy here. Bounded by that red. And that's the actual energy that will be converted into kinetic energy of the bullet. So having said that much, these are the things that the fact that the loading pattern and the unloading pattern are kind of different explains why we may have energy losses. Why we don't get what we predict in terms of the theoretical flight. Okay? So this little region here, that little region there, right, actually is energy we can't account for really. It's like a loss or energy that's not available in our propulsion system. We lose that amount. If we load up to this point, then we release. So we could assume, if we ignore the hysteresis effects, we'd be assuming that all the energy we stored here, we actually get back. If we ignore this hysteresis effect, because this little green part, this black part here will be we have your losses. And I'm saying that if we do our calculations with the assumption that all energy stored is converted into kinetic energy, when in fact this is the energy that actually is converted to kinetic energy, then we'll be basically overestimating how much energy we have and overestimating the velocity of discharge and so on, right? Good. So, in short, what we want to do, so let's draw that graph. Now, let's say that's your graph. What you would have done, you, during the experiment, would have done some loading up. And then some unloading. And what we want to do we'll assume the hysteresis effects, you could do that, are negligible. You could assume that. But of course in the discussion you'll have to say that contributed to error. So you can't speak about hysteresis effects in the discussion if you don't demonstrate what it is with a graph or some of this sort. Again, this is a graph of load against extension. Okay? Now if you assume that hysteresis effect is 0, then this line that you have here will be the same as the line for unloading. The two lines will coincide if there's no hysteresis effects. This line, when it decreases, is supposed to follow this exact line. That does not happen, so you have to explain that. Now, what I am going to do now, I'm going to take that graph and I'm going to show you how you can actually, if you go with that assumption, if you talk about energy stored in the spring now, in the rubber band, you come and you do the same thing again. So all I look at for now will be the forward curve, the loading curve, right? So look at the loading curve. I change the loading curve to blue. Alright, so I do the loading curve like that. And I will ignore that's why I draw it very faint. I ignore this curve, even though I know it's there. I'm ignoring that curve, right? So the second part of the lab actually designed to find how the load, how the energy stored. Remember, this is a force. Where is the extension? So at this value of E, at this value of extension here, E, let's call it E, 1 for instance. When you come here, you draw a line. Once you have gotten this graph, you draw a line up here, and you could count the squares basically, and if you draw a good graph and find the area here, and you could say, well, the area bounded here is the energy. Area bound up to this point is energy stored by extending the rubber band by an amount E1. Right, so this is how you actually get in how the energy varies with extension. How the area therefore bounded varies with extension. So you'll say variation of energy with extension should be seen as the variation of area bound by curve with extension. So in other words then, when you extend to a different value, so you extend to a different value now, E2, then you draw a vertical line up here like that, and not only this area here, but even the place before. All of that now is the energy stored. The area here corresponds to the energy stored when you extend by amount E2. Right? So that's this curve is, once you get this curve, you are showing the instructor, the person marking your lab or whatever, that this curve that you got also will furnish you with the information to find how much energy is stored in the system. How much is actually accessible for being converted into kinetic energy is a matter up for discussion. Right? So I hope you understand what you just did here. So making the assumption that as the case, you will see the energy stored, right, at a value E equal to E star will be equal to the area bounded by loading curve, extension axis, the line E equal to 0, which is the load axis, and the line E equal to E star. So let's say E star happen to be here. We draw a line up from E star, draw a vertical line, and this whole area bounded here, that's the curve, that's the line E equal to E star. This is the line where E equals 0, this is line here, and then this is actually the extension axis, right? That's that line there. That area bounded there, total area, that will be the energy stored. So once you get this graph, you've gotten that. So just need to mention, after this describe the procedure to get this curve, just need to mention that, you know, if you want to find the energy at any particular position, is what you're going to do. So now we want to actually find the second part that deals with the trajectory. Okay? Alright, so let's go to the part that deals with the trajectory now. Right, so you need to know energy stored in it. We have to find the trajectory. So to find the trajectory of a fixed mass file from an elastic energy based system at an angle of 0 degrees is horizontal, but we actually made our system for propulsion already, where we use clothespins and a level and a rubber band and so on. You have to draw those diagrams. If I don't see those diagrams, I cannot help you. The person looking at your lab must see the drawings and understand what they're trying to achieve. Okay? So, alright. So what we had our lever, basically, and we had a clothespin. We were holding our bullet, and we extended a rubber band like this. So when you all build a system, I advise you all to take a force meter, and when you pull the bullet in this position and clip it with the rubber band, you'll have recorded the force that you have to pull it with to get to that extension. Then you're going to use that force to correspond to whatever force it is. Let's say this is the force you pull it to, because it's very difficult to measure the extension of a rubber band. So let's say that's the force you pull it to. You'll draw a line across to here of your graph, as you'll have obtained. Draw a line down, and you know what is its subsequent extension. Right? Once you get a subsequent extension, you can find the kinetic energy by finding the area under this graph up to this point. So you call it energy, well, E star. Okay? So, for the next part, we have plan design. You're going to say, well, use a theory and say, well, E star, which is the energy stored in the rubber band, will all be converted to initial kinetic energy of the bullet. Alright, that's when it's being released. Right? So we have to, of course, weigh I, that's equal to, therefore we say E star is equal to M of the bullet, the rubber band, of course, and V squared on 2. So if you want to get the discharge velocity, we'll say that the discharge velocity V will be equal to E star on 2 2 E star on M, that will be V squared, so you find the root of all of that. And that will be the discharge velocity in theory. Of course, we know that all energy isn't converted into kinetic energy, so this value will be this velocity here actually will be an overestimate, because we assume we have all the energy, we get all this energy in. You won't get that much in, right? Being converted to kinetic energy. Once you get that now, we say, let's look at our setup for experiment. So you have to draw several diagrams, okay? And here I try to draw some of them for you to see them, okay? So you must draw where your target is, right? So you fire a gun at distance X from your target. So you have a target position here, right? Use the line of sight of the laser to establish a horizontal position, right? So this actually is a lever, and when you release it, instead of following a straight line pattern due to gravity, its trajectory will vary. So at this value of x, you get that value of y. So you have to show what the values of x and y are by some kind of diagram. Okay? And then, for a given extension, because whenever you put the rubber band back in this exact same setting, we are assuming that it has the same amount of energy stored in it each time. So you will have a table, right? Let's say let's call this position 1. So you'll have for position 1, right? You will have what the area under the graph is, and you'll calculate what the discharge velocity will be. Of course, in your plan design, you'll have the formulas I just showed you all, where you have V will be equal to the the area under the graph will be equal to mb pi squared on 2. So 2 times the area under the graph all over m will be equal to v star squared on 2. As that area has to correspond to the extension, right? 2 a and m is equal to v star squared, and therefore v star will be equal to root of 2 a all over m. This is the area under the graph. Nice. So once you get this particular setting for position 1, what you'll do, you will step back further and further from the wall. So you'll be varying x1 to get different values of y1. So you have a table then, right, where you have for position 1, this table 1, for this value of v star, you will have x1, and you will vary it perhaps, I don't know, 10 centimeters, 20 centimeters, 30 centimeters, 40, 50, 60, 70, 80. You're saying? And then you'll have a value of y1, a value of y, right? A value of y at that point. So you'll have whatever it is, y1 here and y2 that corresponds with that, and so on and so forth and so forth and so forth. So what you'll be working on is the trajectory of the graph when the rubber band is pulled in the bullet and the bullet loaded at position 1. So what you will do, you have to draw a diagram showing that. Show this is actually a vertical target. You show that this is actually a displacement. This is the line of sight, but this is your actual trajectory, right? As you go further away, you just put this guy further and further away. Try different values, 10, then 20, then 30. So the x value is going to vary, right? You'll get different values of y. You'll drop the different values of y as I pull it back. Right. So all this would be for one position. So you're actually taking the entire gun and you're stepping backwards. So if this is from the front of the gun here, the here is x1, as you see here. Okay? Now, it was in other positions. Like this might have been position 1. So you have a rubber band stretched all the way to here. So there's a lot of energy stored here in this position. So when you release this, you'll have more energy to start with. So this will correspond to a different position. Maybe I should call this 1, this 2, and this 3. All the while you ensure you have a level. This is supposed to be a level, spirit level. And you have the bubble in the middle. So that means that you know it's level. So when you fire, you'll be fortunate where it's supposed to hit and how far it falls and recording that. So I would have done this whole graph with readings here from position 1. We should be like here. We'll change those numbers to 1, 2, and 3. Right? So let me just change those numbers there. Right. So I'll change that 3, 2, 1. So in position 1, which is like this here, you get the energy stored, and this will be our constant value for that position 1. Right? So I put V1 star. For position 2, your rubber band is stretched to a longer point so that you know that you have more energy stored and you have a different discharge velocity. That will be V2. The same name for V3, but you just repeat for things like that. What you're actually doing, this is actually a trajectory. This trajectory, by stepping back further, you're actually getting a new value of x and you get an x corresponding value of y. Right? And you can do that for all three positions. Right? That's what they're supposed to do. Once you show me that, and I'd like to see some diagrams, please, to show what you did, I don't have a problem. Your problem is, first of all, you didn't do the unloading graph, but that's easy to work with because all we need to say, we can assume that the hysteresis effects are negligible. In your plan design, you will get licks with it and you can't do nothing about it. I will take up marks, A mark for not doing the unloading section. But in your plan design, in your ANI, you can say you did not do the unloading because you felt you want perhaps the unloading effects. You're assuming that the unloading effects are just the same, or it would have unloaded along the same curve as it was loaded. You can make that assumption, right? Which is saying that all the elastic potential energy is converted into kinetic energy of the system, right? You can make that assumption, right? So you see you have a level, is your clothespin holding anything and so on, and you have your laser again pointing to your intended value of y, and you have your value of y there. And of course, you can measure the distance here by whatever you want, and this one by whatever you want. Okay? I will propose a laser distance meter. Right? So that's that part. Once that is done, all you do is write your comments now. Okay, so let's see what the ANI is looking for. So let's go to the ANI. Sorry. Let's go and look at the ANI. What are you looking for in the marks for ANI now? Okay, so I think this is the PND was. Let's look at the ANI. Implementation. Let's see what Mr. Kukaradi was looking for in the implementation. Okay, so let's step across there. So I expect to use some kind of free body diagram just to say that the tension stored in the elastic member is equal to the force on the force meter. Alright? Student correctly plots F versus extension because remember it is a polymer. That is to say, I expect to see the shape that I showed you. Right? Polymers like rubber band and so on, like rubber, has that kind of shape. This general shape. So some of you will actually have left out those points of the line. No. Include those points on the line. That's the shape you expect to get. Right. Next, I want nice neat graphs, please. Please. Right. I had some horrid diagrams. People don't use ruler and that kind of thing. We do that in science. Alright. So let me come back here. And I said, right. So when I say correctly plot, that's important. If you think you have a straight line and try to do a best fit line, you'll know some points, and that won't be a correct plot. Right? Many of you get licks for that. So then correctly determines the area under the graph. You have your scale and show me how you get the area under the graph for any particular position, E. Right? So then uses the law of convection energy to determine the velocity of projection. That's the formula I'm talking about, where you use that the area is equal to mv squared and 2. And so 2 times the area and m, the root of all of that will give you a velocity of discharge. Right? So I'm looking for that. Right? So you have to say, you have to mention the law of conservation of energy. Right? And say it's an estimate. Right? And it correctly determines y theoretical at different values of x. Now, this part is quite simple. This part, right? Y theoretical. Oh boy. Right. So we know that now. For y theoretical, if you assume the discharge velocity is given by this value v1 star, what you will say is that we know that for a projectile, that movement in the x direction, x is always equal to u cos theta by t as x displacement. And y displacement is equal to u will simplify by sine theta by t minus gt squared on 2. So if I want to find out y varies with x, I want to eliminate t. So I'll get that t is equal to x all over u cos theta. I want to find out y varies with that. I'll take that x and substitute in this equation. T, sorry, substitute. Anyway, I have t, I'll put x on u cos theta. And I'll get a relationship between y, x, and theta. So I'll get basically that y. Now use the discharge velocity. This u is the same as the v star I will calculate here. So this is actually going to be u sine theta. But t was what? X all over u cos theta then. That's u sine theta by t, x on u cos theta, minus g into on 2 into t squared on 2. So t squared will be x squared on cos squared theta. Right, so that's x squared on u squared, sorry, cos squared theta. Right? I want to simplify that. We know u into u is u, and sine to cos tan theta. So your theoretical, remember, what do I predict to get? So you get y, your theoretical, for will be sine and cos tan theta multiplied by x minus, this actually is g x squared on 2 u squared cos squared theta. Now we said our angular projection, we're going to make sure it's always level, is going to be 0. So you have to write that therefore, but since theta is equal to 0, we know tan theta is 0, that means tan theta is 0. And cos theta is equal to 1. Right? Everybody knows that, or should. Alright? Right. So then y theoretical becomes therefore y theoretical, so you have to explain all of that in your plan design. Y theoretical, because that's how you plan to do your lab, will be tan of 0 is 0. Right, so you have y x is equal to a half by g by x squared, cos of 0 is 1, all over u squared. That u squared is actually v star. Right, that's the velocity which you're launching at. So that's equal to a half. Let me summarize that. So we now have therefore y theoretical is equal to g x squared all over 2 u squared. Right? So the different x, y theoretical is supposed to be that. Of course, you'll do the experiment and you'll measure what y theoretical is. Right? So you're going to get this from your experiment. Is y actual, where you measure where the target hits below the laser, and the distance is y, and the distance across, of course, is x. Okay? And then you're going to correct, this is actually actual on readings. Right? You could do that, you suggest in your plan designer, you'll do it for 2 other readings. But you actually do it for 2 other positions in your plan design, in your ANI. So you have for 2 and 3, you'll have different values of V and so on. Right? but you must have your diagrams. I have to see what X and Y is. I have to see how you get your Y. I need to see that. I need to see different positions and understand that when you have 1, 2, and 3 in your table, what that means, right? You need to show me that you're launching to that level, right? So I'm trying to show how it is and rubber and attach to the mass and so on, right? You also have to find the mass of the bullet and so on. Okay. Now, what I'm looking for in the marks again, let's go back. New section. I don't want to take too long because these videos take a little time. Right. So explain differences in Y theoretical and Y actual. You have to factor in what? Drag. Have drag. You explain what drag does. Right? Drag, what you'll be writing basically, what we know is that what? The drag force increases with velocity. Okay, that's a little too thick. Let me get a little baby thin guy. Right? You know, F drag. The faster you travel, you have a various velocity. Right? Let me see. Increases with V. So the experiences of force that kind of slow you down. And explain different in theoretical, right, by hysteresis. This one will be basically that the hysteresis make it unclear as to how much energy is actually converted into kinetic energy. Right? And then they must explain why some measurements may not have been so exact. Right? Some little things you could explain that. So you must have Y theoretical and Y actual in the same table coming down the road. Right? And then if you're hitting a target, you could actually suggest something you use to actually hit the target. Right, so also to see a free body diagram. A free body diagram will take on this form. Right, so if I was to try and draw a free body diagram, let me get a grid. Right, a free body diagram. A free body diagram will see how it's a the apparatus. So you will have a force meter. And a force meter. And you have a rubber band. And then a rubber band you'll have your slotted masses. Now you see the slotted masses coming on the road. Slotted masses. Now, I was going to kind of draw a diagram showing you a free body. So, if you draw a rubber band, what I want to show is that the tension here, if you didn't would read.
Necessarily about the away goal in that moment.
right? Whatever reading you see here is equal to tension in the spring. Okay? So, what we tend to like to do, if I just draw rubber band as a free body, rubber band under the force here, there's a force pulling rubber band upward, there's a tension in the spring here, and there's a force pulling the rubber band downward, as the weight of the mass. Right? And F net is 0 on it. That's why it's not moving. So when the load reaches a certain point, it isn't working at that point, the weight is equal to the tension. And then of course, the tension, as far as the force meter is concerned, is the same tension it measures. Right? Measure the same tension. Right? Measure the same tension. So as far as he is concerned, right? The force pulling him down, the hook doesn't move any further. So the force pulling him down, which is the tension, is equal to the force pulling him up, which he measures here. So when I go to your mark team and tell you, draw a free body diagram, it'll show me the rubber band under the influence of the forces, a tension in the spring and a weight here. Right? Weight. Well, this weight actually includes the weight of the rubber band, but ignore the weight of the rubber band for this. Right? So in this here, this is actually weight of the masses plus, so make it ignore, so I write it very small, weight of rubber band. Right? This is negligible compared to these masses. Right? So once you get that, you're telling yourself that whatever you read here, therefore whatever you read off here, that is the load. Right? Whatever you read off here, that's your load. So that's why I say you try to show that. Right? Use a free body diagram to show the tension is equal to the force. And what I would suggest to do it actually in the draw that diagram in both the P and D and A and I as a sketch. A free body diagram, it helps. Right? Now, having said that much now, let me just do one more thing. And that is to say, with your diagram, you have to draw, you have to draw this thing suspended on some kind of system, I suppose. Right? So, I'd like to believe that you'll have some kind of retort stand. Have some kind of retort stand, and you have to show, of course, you have some kind of ruler next to it, some kind of ruler. And you must show master diagrams to show, well, what you're very interested in is the position of the rubber band. You want to see where that is. So, of course, you must make sure this is plumb. Make sure it's vertically level by using a level. Alright, level as a bubble like that. Right, make sure the bubble like that is in the middle. Right, use a level like that. You need diagrams, right? I don't like the diagrams that you all give me. So You show this a meter rule here, and you show how you're getting your readings, right? So you're getting your extension. You show with no load, we have no weight hanging where it is. When you add the load, where it end up being. This is a free body diagram here. You should never know. You're reading off here. So you're reading off your extension here, right? Original length, it might be like this. And the original length, so that this part here is your extension, right? You must have a diagram showing that. You must have no load, that was the length. When you add the load, this is what it is. It gets a little longer, right? And you must say hang the ruler plumb. So this is how you measure the extension. And here is where you read off your load. And that's what you're actually tabulating. Extension, load, right? And then making your table. And you really should do the increasing and decreasing. You should have a table saying increasing, and if a table saying decreasing, right? Extension load is decreasing. You should have had one of those. So what I want you to do is, please do some renovations on your things I could give you the full set of marks, right? I want you to look now at what they're looking at in the ANI mark scheme. So I'll go back to that quickly. What's the actually looking for? Alright. Alright, let's see. Right, so like I said, you must have a method showing you changing a manipulated variable. I showed you that in the graphs. Show you're getting your energy with extension, that's the area, or the area with extension. Show you're getting your force with extension, that's from your graph. Right, it's showing how you're changing your load and your rubber band changes and you measure the extension. Results, how you treat the results? Well, that'll be a table basically. Expected results you expect to get. Show me the results. And you have precautions. Well, you need to have some safety, of course. I have some kind of safety concern. I want it to be stretching rubber bands with bullets. And you could be hitting people. Okay? And then you figure it out. And you have an analysis and interpretation, a discussion, or the calculations and so on, the trends and so on. Limitation and source of error, so this is where hysteresis will come in and your drag and all of that. Right? So here you have a hysteresis and your drag. Right? And reflections, you refer to it having the green rectangle on top. Relevance to life. I can actually give it relevance. Right? If you understand how things behave in flight, we could do a lot of things with it. Impact of knowledge gained from experiment. How can experiment be changed and improved? So of course, we want to minimize things like hysteresis and drag. You may want to do many rubber bands and find an average. You know. And get more accurate ways of determining velocity. Your conclusion must be stated and related to the aim. So you must make a statement talking about how the conclusion, how energy varies with extension, how your trajectory varies, and so on. Okay, so I think this is simple stuff. You must have all these headings, right? You must have all these headings. I have to explain what hysteresis is, of course. Right, hysteresis is the difference the graph follows, and I have inside of there data so you can write about how the hysteresis works. Okay, well, this is the end of this video. right? I'm giving you until Monday to make all the changes. So they come, I have your marks, your preliminary. If this goes up, you don't do very well in physics. This is a serious part of your lab, right? If you change it on Monday night, I'll take your changes, right? That's it. But you all really have to give me something better. Some of them have more changes than others to make. I want nice, neat diagrams. The diagrams must show the method they're using, right? Okay, I think I've done enough. You all have a wonderful day. Goodbye.